Testing, testing, 1, 2, 3. Testing, testing, 1, 2, 3. Testing, 1, 2, 3. Alright, audio sounds good. Let's get it. So, hello everyone. We're back at it again with another problem. Trying to conquer physics. The only way to learn and grow, just like when you're lifting weights, is to lift weights. And so, if you want to get better at physics, you gotta do physics problems. And today's problem deals with energy. And so we begin with the setup. So what it looks like is we have a pinball machine launch up a ramp consisting of a spring force constant K, and this is 30 degrees up a ramp. And the ramp's length is L. Oop, this is actually length L. And so what's interesting is this setup is actually set up for these next 3 questions. Um, We'll see how far along we get to decide if we want to do it all in one sitting. We might just do one at a time, just 'cause it's a little late. But the first problem says, you want to launch the pinball, the sphere with mass m and radius r. So this has mass m, just zoom in a little bit, radius r. And it says, so it barely reaches the top. So the setup is, we basically want to launch this pinball such that the ball starts here, and then it ends up right at here. Boop. Initial state, the final state. And it says it just barely reaches the top of the ramp without rolling back. What distance should spring be compressed? You may assume friction is sufficient that the ball begins rolling without slipping immediately after launch. Okay, so what this is saying is that this ball is going to be basically rolling up, then rolling back down. And so we're given 5 answers as usual. Square root of 2 mgl, 5kl, 5kr. This next one is square root of mgl over k. The next one, square root of 2 mgl over k. The next one, square root of mgr over k. And the last one, square root of 2 mgr over k. Okay, so we get a big hint because we know this section is energy, but that would have been one of the go-tos. So usually the go-tos would be force body diagram or energy. And so what we got to understand is as much as we compress the spring, we basically get energy out of it. And so the equation for the energy in a spring tends to be 1/2 k, and then the distance of compression, which I'll call delta x for now, squared. And so this is usually the potential energy that's stored in a spring for however much you compress it. And basically what we want to find out is what's the distance that the spring should be compressed. And this ball is going to end up rolling up to the top and then stopping as it reaches the top. So normally this problem, it would seem more complicated in the sense that you got to take into account the dynamics of this ball rolling, it transferring potential energy into kinetic and rolling energy, and then getting to the top to potential energy. But since we're dealing with this problem in a way such that there's no kinetic friction, because clearly in the problem it says rolling without slipping, which means that we're not losing any energy to friction, but it is being transferred to momentum. So we could say that we have energy transfer from potential energy stored in the spring to kinetic energy in the ball moving up, and some type of inertial energy. So we'll call it rotating energy, as the ball will begin to roll up it. But when it's at the very top again, we have potential energy in the form of gravity because it stops rolling. And so this neat part about this energy is, since we're not losing energy in between, we could basically skip these parts. And all we got to care about is just the energy stored at the top right here. So we just have to find out the height. And the height we can get using trigonometry, knowing this is L and this is 30. So we know that H is going to be equal to, again, we bust up the SOHCAHTOA. And so we have hypotenuse and opposite from this angle. So we're going to use sine. And so this is going to be equal to L times sine of 30 degrees, which is equal to L times the square root of 2 over 2. This is going to be our height h. So we know that the initial energy here is going to be 1/2 k, and then compressed x. And then when it goes to the potential energy, this is going to be mgh. And so what we want to solve for is this part right here. So we can divide this part out here and get this is equal to 2 mgh over k. And then we take the square root of both sides. I want to make sure to try to include more steps, just so that way we get a better feel for these problems. And is this one of our options? Yes, it is. Oh, wait, I'm not sure yet. We have to plug in h. So what is h? H is equal to L times that. So we have 2 mg L square root of 2 over 2 divided by k. So these two 2's will cancel out, giving us the square root of 2 mgl over k. So something seems to be a little off. Let's try to think if there's anything we're missing. So the way that it's drawn up here, it's the way it's drawn up here. It has the L up top here, because another concern I would have had is this down here. Give us a different response. Oh, okay. So here's actually a big problem I put. My apologies. This is why it's important to just work out these problems and really take a careful look. It's not the square root of 2 over 2. When you're doing this 30 degrees, this is h is actually going to be half. I have to get my trigonometry correct. If you have 1 here, this is a right angle. My apologies. Let me draw it a little better. If you have a right angle, you have 30, this is a 30, 60, 90 triangle. If you have 1 up here, this side is going to be 1/2. This side's going to be the square root of 3 over 2. And so you see this is going to be 1/2 with respect to this. So h is equal to L divided by 2. And so when we actually plug that into here, if we ignore this, we take this stuff back down. Let's just erase the bad parts. So we're down to here. This h is going to be equal to the square root of 2 mg L over 2 divided by K, which is equal to, and so these twos would cancel out. You're going to get mgl over K. And so now we do have an answer here. So in this case, we got lucky that the multiple choice was able to help us out to make sure to correct us. And that's important to always check your work as you move along and go along. Notice how, I had this incorrect part and I revisited, trying to check my work. What could be the problem? I think this is an important skill to have, probably more important than just following algorithms, because there's mistakes that you can make along the way. It's going to be useful for debugging, even in programming. Try to find out where you went wrong along the way. So yeah, I think in terms of time, we could continue on into some of the other problems. Um, so yeah, we'll keep going. Okay, since we have our answer of compression, this next problem states, what is the speed of the ball immediately after launch? So we have GL for A, B is 2 over 5 GL. All this is in the square root part. 5/7 GL. 7 over 10 GL. 10 over 7 GL. So we know GL is going to be an important factor to this, but it's okay. So what we care about is the energy initially stored in the spring. Again, it's going to be 1/2 K delta X squared. And we just solved for what delta X is, this. So when we plug this back in, we can see that the total energy stored is going to be the square root of mgl over K. And since we take the square root of a squared factor, or we square the square root, we get 1/2 K over K for this bottom part, which will cancel out to 1 times mgl. And so our energy is just 1/2 mgl. Now this is pretty interesting. Just think about this for a moment. What was important is the length of the ramp. It actually didn't depend on what angle it was, and it also didn't depend on the spring constant. That's just an interesting thought. Um, what was more important is the energy to get to the top. And that actually makes sense. Oh, but L is not related to the top. Hmm. I'm trying to think a little bit more if we're missing any factors. No, that makes sense so far. Okay, and so to then ask the problem is immediately after the ball gets used, its potential energy transfers immediately into velocity before it starts rolling. And so what's the equation for kinetic energy? The equation for kinetic energy is 1/2 mv squared, right? And so we could set these two equal to each other. We have 1/2 mv squared is equal to 1/2 mgl. You can cancel the m's, cancel the 1/2. We're just left with v squared is equal to gl, and that v is equal to the square root of gl. And so clearly from what we have over here, it would be the first one. For some reason, I'm still a little skeptical of this. We're making a big assumption that our first part is correct. And so we're just going to continue on with it. I'm not sure if there's a solution manual to this, but I would go along with that our solutions look correct. And we're just going to say they're correct. We'll have to verify it later on. But in the meantime, we'll go to the third problem. And then it says, now suppose the ramp is waxed, so there is no friction. What is the distance the spring should be compressed this time? Giving the same responses. And so what's really interesting about this problem is, um, assuming that there's no kinetic energy in either case, in this case, we still don't even have, um, we just don't have static friction, but, and because it's waxed, we can make the assumption that there's just no friction overall. And so total energy overall, it should be the same. So when it's asking how much the spring would be compressed to reach to the top, ideally it should actually be the same compression to get to the top, because the before it was potential energy getting converted along the way to kinetic energy and then rolling friction, rolling energy, and then potential energy at the end. And so with the new ramp being waxed, we're just skipping that rolling friction part, but it's all still kinetic energy getting to the top. And so it should actually be the same. So my guess would just be the same answer we had before, which was B. And there we go. That is the pinball problem in a nutshell. I guess since I'm here and I technically do have the answers somewhere in the back, I will make sure to verify that. So if y'all don't mind sticking around just for a few seconds while I look for it, I will double check it. I'm assuming they have the answers. We have sample tests here. There's an equation index. Yeah, I don't see an answers thing here. But if anyone would like to test me or check me on that, please do. And if there's any problems, let me know in the chat. Hello world. Send a message to myself. Alright, but in the meantime, we're gonna call that a wrap. And y'all have a good night. Keep shining, stay learning, and take care. Bye bye.